So this first one here is find the identical expression for the following: sine times secant plus cotangent. And so let's see. So question 1, sine x times secant x plus cotangent x. It looks like in a weird place, that plus. There we go. And that's going to be sine x times, and now I'm going to use the reciprocal identities, so cosine x plus this one here is cosine x over sine x, and then I distribute the sine x, so I'm going to have sine x divided by cosine x plus, and then that one is cosine x because the sine x of course divides out, and then I check the possible solutions here, and it's going to be the first one because this one here of course is tangent. Okay, the next one, this one here is really similar to that one, and on this practice exam I may not do all of them if it turns out that the following problem is really similar. Here I'm going to make an exception. So sine squared x times cotangent squared x plus 1, and that equals sine squared times, and here recognize that that is a Pythagorean identity, so cosecant squared x. As I said, that's a Pythagorean identity. And of course the cosecant is the reciprocal of the sine, so sine squared x times 1 over sine squared x, and that of course is 1 because the sine squared divides, and that one is one of the possible answers. By the way, even if I didn't know that particular Pythagorean identity, I can do it as follows. I'm going to change the color on this one. Even if I didn't know that, I could do the following: equals sine squared x times cosine squared x over sine squared x. That one I do have to know, plus 1, that is the ratio identity. And then of course on the first one the sine squared divides, so it's going to be cosine squared x, and on the second one when I have distributed it, that is sine squared x, and that one I do have to know, that Pythagorean identity I have to know, even if I didn't know the other one. I would have to know that one. And when I check the answers, that answer 1 is indeed there. So here's question 3. So let's see. See instructions for these here. You only get points if you show the algebra in the editor box. Find the identical expression for the following, and so this one is 1 minus cosine to the 4th divided by 1 plus cosine squared, and I give away here that this one is already the correct answer. If I didn't do that, you would have to figure out each one of them is not the correct identity, therefore it would be a false statement, and only this one is, and that's actually more work than showing the algebra behind just the correct answer. So I'm going to pick that one, And so that one is going to be 1 minus cosine to the fourth divided by 1 plus cosine to the squared theta equals apparently sine squared theta. Okay, and then I'm going to open this one here, and let's see what it says there. Okay, there it is. Show that this is an identity. Hint: the numerator can be interpreted as a difference of squares. Okay, I guess I can just stay right here and don't have to go back to that writing program. Alright, so the numerator can be interpreted as a difference of squares, so the denominator is going to turn out like this: 1 plus cosine squared x and 1 minus cosine squared x divided by 1 plus cosine squared x. And then I should say here left side. Okay, and that was difference of squares, and then I recognize that this one here divides with this one, so that one is the answer on the left hand side, and I see that that is sine squared because that is the Pythagorean, or one of the Pythagorean identities, and this is what I ask our students to do. Type this out just the way I do it. You don't have the luxury of handwriting it. Using an equation editor would be asking too much. You don't have to figure out how to use an equation editor just for this problem or for these problems, but just typing straight on the keyboard is required. And then you can leave it either in this document and email it to me, or I can go back to the test and go to this last question, and this is for question 3, where I just added that in. Okay, I'm not going to do number 4, 15, and 16 because these would be done in the same fashion and would be also showing the kinds of identities that they're doing in this chapter. So I'm not going to do number 4 here. Let's see, number 5 says, use a graphing calculator to determine if the equation appears to be an identity or not by graphing the left expression and right expression together. So I'm going to go to the graphing calculator. Okay. So y equals, and then I'm going to have the left hand side would be cosecant. So I'm going to have, I have to shift this a little up because there's, oh, there we go, that's better. Okay, so cosecant is the same as 1 over sine. I don't have a choice on my graphing calculator, minus cosine of x. There we go. That's the left hand side, and then the right hand side is cotangent, which is 1 over tangent. So again, I don't have a choice. I have to type it in this way. And then times cosine of x. Okay, and then I'm gonna see that I'm in radians. I could be in degrees. Radians is a little bit more convenient because I can just go from 0 to 2 pi, for example. And scale really doesn't matter. The y minimum, I don't know, maybe I go between -2 and 2, anticipating that I have an amplitude of 1, maybe a little bit larger. And then I graph, and there's the left-hand side graphing. Still the left-hand side graphing. And there's the right-hand side graphing, and that is definitely not the same. And therefore, this one is not an identity. I may want to double check if I actually typed them in correctly. And this one is 1 over sine is a cosecant, and then minus cosine, and the other one is 1 over tangent is the cotangent times cosine. So I did type it in correctly, and this one is not an identity. Okay, question 6 says find an identical expression for this one here, and then hint a perfect cube formula may help. So I'm gonna do that one. I have to move it out of here. So this one said tangent cube a plus 1. I actually have to look at it. And this was question 6 divided by tangent a plus 1. And then I used that perfect cube, so in the numerator, sorry about that bad fraction line, drop that again, there we go, that looks much better. Okay, so that one, therefore, again, when you look at the perfect cube formula, it's going to look like this. Tangent squared minus tangent plus 1 parentheses divided by tangent a plus 1. And then, of course, that divides with that. And now I'm going to look at the answers. And that answer that I just came up with indeed matches one of the answers, the last one there, tangent squared minus tangent a plus 1. Okay. Question 7 says write an expression as a single trigonometric function. So I have a cosine 8x cosine x minus sine 8x sine x. For that one I'm looking at the right hand side, where I have a cosine times cosine minus sine times sine, and therefore I'm going to have cosine plus for that minus. So therefore it's the second one. I don't even need to write this down. This one here is 8x, this one is x, and the original formula says a minus, which then according to this identity formula turns into plus. So it's 8x plus x cosine of 9x, and the first one is correct. Okay, question 8. So if tangent a plus b equals 9, then and tangent b equals 1 over 73, find tangent a. Okay, there are several ways of doing it. There's the crude way of plugging it into the calculator and see what works. But the proper way is to do the algebra, and here the idea to get is, where do I actually start? They give tangent b and then they say something about tangent a plus b. Well, that means there must be some kind of identity that I use, and in fact there was in the last problem. Right there it is, tangent a plus b equals this stuff here. And one of these here I'm going to write down as tangent b, 1 over 73, and the left hand side I will eventually write down as 9. So that's what I'm going to do. Again, I need to push it out of the way so I have space. So question 8, where I'm going to start out with tangent a plus b equals fraction bar, and then I have tangent a plus tangent b divided by 1 minus, look carefully at the identity, tangent a times tangent b. And now I go in there and use what is already given. The left hand side is supposed to be 9, and on the right hand side, let's see, there's a pretty thick fraction bar, but I'll use it rather than hand drawing it. I'm going to have a tangent a plus 1 over 73 minus 1 minus tangent a times 1 over 73. Okay, let's see, there are several ways of doing it. One would be algebraic, the other one would be just trying something for tangent a, see what works. But first I'm gonna get rid of that 73 out of these denominators here, so I just multiply the the numerator here with 73 and this denominator with 73, and of course I didn't change anything in the value when I do that, so I don't have to do anything on the left hand side. Plus 1, and this one here is 73 minus tangent A, and my 9 got a little bit too small. There we go, looks a little better. Okay, well, at this point I could solve for tangent A. Takes me a little bit of algebra, or I could look at what kind of answers I have. So tangent A could be 8, 9, 10, 11, or 12. I don't know if that's gonna really help me. I just do the algebra. Okay, that's kind of going to take a moment here. 9 times 73 minus tangent A. That's of course something when you start a problem that is hard to see which problem turns out to be really easy and which other problem turns out to be, well, taking a while. In this case, this one here will take a while. Let's see what we get. 9 times 73 is 657, if I'm not mistaken, minus 73 tangent A. Whoops, that's not true. Minus 9 tangent A equals 73 tangent A plus 1. Actually, that's not too bad. Subtract 1 from this one here, so that's 656 equals, and then 73 minus plus 9. 73 plus 9 is 82 tangent A, and then tangent A, divide 82 into 656, which is 8. So the correct answer is 8. Okay, and the next one says, okay, I was interrupted for just a moment. Okay, so I have cosine 2x, and I'm supposed to express it as cosine plus x, and then using a formula for the cosine of a sum. That formula for the cosine of a sum would be this one right here, so I'm going to use that in a moment. Cosine times cosine minus sine times sine. Remember that it's at a plus and for the problem at hand. Okay, let's see, there it is. So this is question 9, and I'm supposed to express cosine 2x as cosine x plus x, and then I'm supposed to use a sum. So I'm going to come up with cosine x times cosine x. This is the sum formula that is given in the test, minus sine x times sine x, and that is of course cosine squared x minus sine squared x. Notice this is not the Pythagorean, okay, because there's a minus. Pythagorean has a plus. And then I excuse me, then I look at the correct answers, and indeed that is this answer. It's the correct one. And actually, essentially what I did here is the problem told me to find write a formula for this one. Essentially what I did here is I found an identity. Cosine 2x is the same as cosine squared minus sine squared. So with a little bit of a hint, that's what I did. Okay, question 10, which says that I'm supposed to express this one, sine of 90 degrees minus x plus sine of 90 degrees plus x equals. So for these ones I'm going to use two sum and difference formulas. One of them is that sine 90 degrees minus x is the same as sine 90 degrees times cosine x minus cosine 90 degrees sine x, and the other one is plus sine 90 degrees cosine x plus sine sine cosine 90 degrees, sine x, and that therefore, of course, this is a 1 here, so that's a cosine x. This one here is a 0, and this one here is a 1, so it's plus cosine x. And this one again is a 0, so I'm going to come up with 2 cosine x. And when I look at the right answers, it's this one here. Is that what I did? Yep, 2 cosine x. Okay, so problem 11 says, from the list below, find the expression equivalent to sine 60 degrees, and then it gives a few choices here. And then, of course, there's the double angle identities in here for this particular problem, so that must have to do with it. And the only thing that, when you look through this one here, the only thing that would be applicable to the sine 60 degrees is sine 2a, which would make the a 30 degrees. So sine 2 times 30 degrees, and then that would turn into 2 times sine 30 degrees cosine 30 degrees, and there is the correct answer. And the next problem, if tangent A equals negative square root of 5, find tangent 2A. Of course, that would mean that I need a double angle formula for the tangent, and it's in the previous problem, so tangent 2A is going to be either this or this. The two are, of course, totally equivalent. I'm going to take the first one here. It's quicker to substitute in that negative square root of 5, so I'm going to do that. And I need to look at it too, and then it's going to say for, let's see, question 12, that tangent A equals the square root of negative 5, and then find tangent 2A, and then I'm going to look at that formula that is given on the test and the exam, and of course it's in the book too. Again, I need that fraction bar, and maybe I should make this a thinner line. There we go. Yeah. Alright, and then it says 2 tangent A and 1 minus tangent A squared. And then I plug in the numbers. So 2 times negative square root of 5, 1 minus negative square root of 5 squared. So equals, let's see, negative 2 square root of 5. Need the fraction bar. And square root of 5 squared is 5. It's not 25, it's 5, because the square gets rid of the square root. The negative squared is a positive, so I'm going to have 1 minus positive 5, which is going to be a negative 4. The negatives, of course, divide out, and it's 2 over 4, which is 1/2 square root of 5. And I'm going to look at the possible answers, and that would be this one here, square root of 5 over 2. Okay, and the next problem, question 13, simplify the expression. I have done this several times in eLive, and I would just do the following. I would do cosine pi over 6 is the same as cosine of 30 degrees, which is the square root of 3 over 2, and sine pi over 6 is the same as sine 30 degrees, which is the same as 1/2, and then plug in those numbers and I come up with the right answer. And previously I was thinking, gosh, why is that problem in there? What does it really have to do with any of these identities? Well, it turns out it does. Notice that it says cosine squared minus sine squared, and I go back a couple of problems, and here it says cosine squared minus sine squared, which means this one is cosine 2a. Let me double check that. Yep, that's what I have to do. So I'm going to use this identity right here, which means it's going to turn into cosine 2a. So I'm going to do that. So this is problem 13, and it says I'm supposed to simplify this expression, cosine squared pi over 6 minus sine squared pi over 6. And again, I'm going to look at this one here. So this one right here will therefore be cosine 2a, so cosine 2 pi over 6, cosine 2 pi over 6, which is cosine pi over 3. And now I do need to have memorized my basic numbers. This one is the same as cosine 60 degrees, and I do need to know that this is 1/2, which is one of the possible answers. So when I go down here, there it is. There's the correct answer. Even if I don't have this one here memorized as being 1/2, well, I can legally cheat, so to say, taking the graphing calculator, making sure that I'm in radians. I am, and then just type in cosine pi over 3, and there's the 1/2. Okay, the next problem. Okay, so question 14. If sine A equals 4/5 with the angle A in quadrant 2, find cosine A over 2, and apparently this has to do with half angle formulas, so I have to do something with this one here and substituting that one in. Okay, I'm going to push this to the side so I can work on this. Question 14, and so this one says sine A equals 4/5 with A in quadrant 2. Find cosine A over 2, and I'm gonna choose that. I'm already using that identity, so the square root of, there, a little thinner, square root 1 plus cosine A divided by 2, and there we go, and then a plus minus in the front. Now I cannot plug this in straight away, the sine A equals 4/5, because it says cosine A in here, so I have to do something. Well, this one here is going to give me a clue. The A in quadrant 2, as well as the nice integers 4 and 5, is also going to give me a clue. I have to go back to a previous problem and perhaps another chapter that I remember. So here's my coordinate system, and then I'm going to put in here, let's see, I probably changed the color on this one. There we go. Okay. Here would be my angle A, right there, because it says in quadrant 2. So that's my angle A. I'm going to go back here, and there we go, and there we go. And now 4/5 means that this one here is 4, this one here is 5. This is how the sine is defined. And then I look at this triangle and I say, hey, that's a Pythagorean, of course, because it's a right triangle, and if this is 5, this is 4, and this here must be 3, because 3 squared plus 4 squared equals 5 squared. That's what I said about these here. These integers kind of give me a clue that this one here is going to be a 3, and from that one I readily know what the cosine of A is cosine A equals 3 over 5 adjacent over hypotenuse, and I'm in quadrant 2, so I have to put a negative in front of that. Okay, so equals plus minus square root of the fraction bar. I think there's going to be a green fraction bar now, but that won't matter. And then I'm going to have 1 minus 3 over 5 divided by 2 square root. Okay, as you see, let me go back here for a moment. As you see here, I have to know this is how I attack the problem, and so I kind of have to keep things like that in the back of my mind, what I learned previously. Otherwise, if I don't know this kind of roundabout way, then I won't succeed in this problem. So anyway, do this one here. 1 minus 3/5 is, let's see, 1 minus 3/5 over 2 is 2/5 divided by 2, which is 1/5. So I'm going to have plus minus the square root of 1 over 5. And then I have to decide between the plus minus. So again, it's square root of 1 or plus 5. And this is where this A over 2 comes in. If A itself is in quadrant 2, so A is in quadrant 2, then I take half of that A, and I'm going to be in quadrant 1. For A, I'm going to be between 90 degrees and 100 degrees, which means that for A over 2, I'm going to be between 45 and 90 degrees in quadrant 1, and in quadrant 1 the cosine is positive. And again, that's something that I have to know, that the cosine is positive in quadrant 1 and negative in quadrant 2. I'm going to look at the possible answers, and there it is, 1 over the square root of 5. I'm not going to do 15 and 16 because that's what I showed earlier for problem 3. And so what's happening here is that this used to be a multiple choice question, still is, with me giving away that the answer is the first one. And then you would still have to show that by typing, for example, taking the left hand side and getting rid of the b over 2 with the half angle identities, cotangent b over 2, you would use one of these formulas, the reciprocal of one of these here, and look closely which one you would choose, and then manipulating the right hand side and see that the left hand side equals the right hand side. And that's basically what a lot in chapter 5 is about. Same thing on number 16. Again, I give the answer away, and then you still have to show that. Okay, number 17, graph the following function from 0 to 4 pi, y equals negative 2 sine squared x over 2. So I'm going to use the graphing calculator and type that in there. Negative 2 sine, I'm going to put parentheses around that, sine x over 2, sine x over 2, parentheses, and this is where I put the square. That's how the calculator accepts it. Then I'm going to go to mode, see that I'm in radians, and go to window, 0 to 4 pi it says. Okay, and then it looks like my amplitude is going to be 2. So I'm going to go from, and actually my amplitude is 2, but it tells me these here that I have to go from negative 4 to 4, so that's what I'm going to do. So, and what I mean by that is that way it's going to look nicer when I graph it. Then it looks kind of similar to what it looks on the test here. That's what I mean. Okay, and I forgot that this here is the scale, which really doesn't matter a whole lot. I can put a 1 there or pi over 2 or something like that. Doesn't really matter a whole lot. Okay, so there it is. Okay, actually kind of looks like the first one. This one goes down to negative 2. Yep. Well, let's see, hold on. Yeah, pretty much looks like that. So it's likely going to be the first one. Let me double check the others. Well, definitely not, definitely not, definitely not, definitely not. And I'm just going to double check that I actually have plugged in the right equation. Yep, that's what it is. So it is the first one. Okay, number 18. Okay, evaluate this expression without using a calculator. Assume the variable represents a positive number. Tangent of the arc cosine of 2x. And they do that in section 5.5. So I'm basically going to do what they show us there. So this is question 18. And I'm supposed to figure out what this is. Again, I'm going to make myself a coordinate system, because that's what they do in section 5.5. And then I'm going to find another color. There. And there. Shift this maybe a little bit if I'm able to. There we go. Okay. Then this one here is the angle theta. Notice that there is no theta in this equation. However, usually I would take tangent of an angle theta. Well, that theta here is that cosine, the inverse cosine of 2x. And so that's how I define that angle. So that means then, I'm going to pull this over here. At least I try to pull it over there. Get rid of this here for just a moment. I don't have enough space. So this one here is the theta equals the inverse cosine of 2x. That's what I wanted to say. Okay, that also means that the cosine of theta equals 2x, and it's the same as saying 2x over 1, and now I can define my triangle as saying that the adjacent is 2x and the hypotenuse is 1. And for the tangent then, tangent of the angle theta, I have to figure out what the opposite is, and then of course the tangent theta is the opposite over the adjacent. So eventually I'm going to have something written as, here's the fraction bar. The adjacent I already know that is 2x, and the opposite here as well by the Pythagorean is going to be, I'm going to move this over here a little bit, a little more space. Opposite equals the hypotenuse squared minus the adjacent squared. So 4x squared, 1 minus 4x squared, and take the square root of that. And there, when I take the square root, I can say I have a positive or negative number, but then the problem it says assume the variable represents a positive number. So I'd use a positive square root, and I'm going to come up with that the opposite is 1 minus 4x squared. Take the square root. So basically, really what I did here is I followed what they're telling me here in a couple of examples in that chapter, and now I'm going to see that indeed one of the answers is that particular one. Okay, problem 19. Rewrite the expression as a sum or difference, then simplify as possible. So 4 sine 7x cosine 2x, and I have to write as sum or difference. It can be argued if it looks more simple when I'm done or not, but that's what this particular problem wants me to do, so it's supposed to look like one of these here. And again, it could be argued if that looks simpler, but that's what it wants me to do, to change it to such. So sine 7x cosine 2x, which is going to be this one here. So that's what I'm going to use, and of course the 4 is just going to be in the front. And don't necessarily look at that this one here or this one is correct, because notice there's a divide by 2, so if I happen to have a factor 2 in there, that could actually divide out. We'll see what happens. Okay, anyway, I'm going to use this one here, and again I need to push it to the side. And number 19 is going to be 4 sine 7x cosine 2x, and then I'm going to use those product to sum identities, and sine cosine is going to be, need the fraction bar first, is going to be sine 7x plus 2x plus sine 7x minus 2x divide by 2, and then I forgot that 4 there, so there it is. And if I really wanted to, I could make that a proper fraction bar, and then 4 over 2 is 2, and then I'm going to have parentheses sine of 9x plus sine of 5x. Okay, so what I did here is I used this one here and just plugged in my 7x, 2x, 7x, 2x, and I come up with, what was it again? 9x plus 5x. Yep, there's sine 9x plus sine 5x, and there it is, except they wrote it. Well, they exchanged the two, but of course addition is commutative. So problem 20. Rewrite the expression as sum or difference and simplify if possible. Well, cosine 90 is actually 0, cosine 270 degrees is actually 0. So I know the answer right away, but what they want me to do is use this particular one right there, cosine, cosine, and then so on. And this is what I would come up with. This is actually the long way of doing this particular problem. And they don't say that I have to do it this way, but I'm guessing, it was just the problem ago. The product to sum formula was introduced, so at this point here, that's what I should be using. That's the product to sum formula. Again, it says cosine 90 degrees plus, cosine 270 degrees, no, times cosine 270 degrees. And that comes out to fraction bar cosine 90 minus 270 plus cosine 90 plus 270 divide by 2, and that equals then cosine of negative 180 degrees plus cosine of 360 degrees, fraction bar divide by 2 equals negative 1 plus 1 divide by 2 equals 0. And the last problem, number 21, I'm supposed to figure this one out here with a sum to product formula. And so this one is going to be 21 cosine 5 pi over 12 minus cosine pi over 12. And for that one, I have to use this one here, and so I'm going to use that and just plug everything in. So that's going to be negative 2 sine of 5 pi over 12 plus pi over 12 divided by 2 times sine 5 pi over 12 minus pi over 12 divide by 2, parentheses, equals -2. Sine, that's going to be 612. 612 divided by 2, which is going to be 6 over 24, so it's a quarter, pi over 4. And this one is going to be sine. That's 4 over 12, so 4 over 24, which is pi over 6. That's the answer, and that particular one is going to be, okay, I see what happens. All right, so -2, and then sine pi over 4 is the same as sine of 45 degrees is the square root of 2 over 2. I see, okay. And this one here is sine 30 degrees, which is 1/2. And so one of these two divides, and I'm going to have negative square root of 2 over 2. And that one is, which one? Did I do this too quickly? Oh, it's the first one. There we go.